Look at my fat cat. I got excited about some math, so I'm going to talk about it. You can sit back down. So I want to talk about descent today. So descent is something that's, you can formalize this definition, but it comes up in a lot of areas, all very related, in algebraic geometry and in algebra. But the basic idea is this. Suppose you have some element, some object down here called R. R could be a ring, for example, and you have some object S that lies above it in some way. And suppose that we have some object, algebraic object, associated to R. Let's call it A. So, for example, A could be an R module or an R algebra if R is a ring. If R is a scheme, then it is going to be a sheaf of algebras, a quasi-coherent sheaf of algebras, if you know whatever that means. So let's say we have some way of going up and getting an object associated to S from A, which we'll call AS. So now a question is, if we start with an object associated to S called B, when does it come from an object associated to A? So when can we descend down to R and get something that when we lift back up is the same thing, up to isomorphism? Because everything is going to be up to isomorphism. There's no equality in mathematics. That's a lie. Quality of sets doesn't mean anything. That's the basic idea of descent. So now I'm going to discuss a specific example, which is Galois descent, which is also very, very cool. So now we're going to talk about Galois descent, and that should hopefully maybe elucidate some of how this works. So suppose we have a field F down here, and we have a field E lying above it. So in this case, that means that E is a field extension of F, or in other words, F is a subfield of E. And we also suppose that this extension is Galois with Galois group G. What does it mean that the extension is Galois? Basically, for us, it means that there's a very nice group action on E. So there's a way that the elements of G act on E via field automorphisms, and G fixes all the elements of F pointwise. So if G is in G and X is in F, then G of X is equal to X for all X in F. So this is what it means to be Galois. Just think of it as a very, very nice group action on E, which has something to do with this structure, with this relation between E and F. So suppose that we have an F algebra. So this is an F vector space, which is also a ring in a way that is bilinear, so multiplication is bilinear. So we have that this is an F algebra. If you know anything about the tensor product, you know that one can extend scalars, and if we tensor over F with E, we get an E algebra. So if you don't know, the elements of this are sums of things that look like this. AI tensor EI, these are just formal symbols, where these are in A and these are in E. And scalar multiplication, if we multiply this thing by E, that's just going inside this thing here. And there are some more technical things about why this is the construction that we want and why we actually need to do this, and we can't define it in a more simpler way. I'm not going to get into that. But needless to say, we can go up. So the question is, when can we go down? So, suppose that we have an E algebra, which we will call B. So, it turns out that the thing we need, the descent datum, if you will, is a G action. So, an action of G on B by algebra automorphisms. So, vector space ring automorphism. You know, it does the nice things. It's invertible. So we need a G action, but not just any G action will do. We need a semilinear one. So this isn't a very standard term, but basically what it means is that normally when you have an action of a group on a vector space, you'd expect it to be linear, so the scalars come out. But here, we also have an action of a group on E. So if we have G, x times V, where x is in E and V is in B, then we get something that's almost linear, up to the action of G on E. So this is G of x times G of V. So that's what a semilinear action is, and it turns out that when we have a semilinear action, if we take the invariance, so now we descend here, what this means is basically all of the elements V of B such that G of V is V for all G and G. So everything that the group action disregards, everything that the group action ignores is in this set. It turns out that if we now go back up and tensor with E, this has a semilinear group action just by acting on this factor. You can check that that is semilinear, and these are isomorphic, so we have descended. This is, in practice, what it means is that there is an equivalence of categories between these G semilinear algebras and F algebras. So intuitively, why should this be true? So the way I think about it, so there is a geometric perspective which makes a lot of sense, but it needs a lot more prerequisites. But the way I think about it is that giving this G action on B, which is compatible with the Galois group action on E, allows you to separate out the part of B that depends on E and the part of B that depends on F. Or rather, you separate out the part of B that depends on F and E. If you go through the details, it turns out that the way you do this does actually preserve the structure when you go back up. So that's the intuition that I have for it. So that is the idea of Galois descent. Hopefully that made a little bit of sense. There's a lot of other types of descent. For example, as I said, there's faithfully flat and the tall descent for sheaves. If you have, for sheaves are the schemes. So if you have two schemes and then you have a sheaf, you can somehow bring it up and, do all the descent thing. But it's much more complicated, so I'm not going to get into it. But I hope you learned something. I hope it was enjoyable to see me talk a little bit about math, and I'll see you next time.